Okay. Good morning, guys. Sorry I'm running late today. Let me get us flipped over here. It's closed. Where did QCam go? There it is. Oh. Camera, resolution, switch over. Oh, yeah, we're in good shape. Okay. So today is the 17th, and I want to do a few things today. It looks like I should probably give a minute or two more for folks to show up before I start talking about the test, because I imagine pretty much everybody is going to want to hear that. But exam 2 is going to be next Friday. And it's going to cover all the stuff that we've talked about since exam 1. It's not cumulative in the sense that I won't be asking any questions that are exactly the type of question I would ask on exam 1. But of course, the skills that we learned before exam 1 are relevant to the homework and stuff we're doing right now. And so in that sense, it is kind of cumulative, right? In the sense that if you don't remember how to differentiate a function, you won't be able to do the sort of things that we're trying to do right now. I'm also thinking about changing the test structure just a little tiny bit, but mostly everything will go the same way exam 1 did. So. Exam 1 is next Friday. Which is 7/24. Yeah, 7/24. It will be in Canvas. Proctored with honor lock. Just like last time, there will be 2 separate assignments in Canvas relevant to exam. I say exam 1, this is exam 2, sorry. Exam 2 is next Friday. 7/24, it'll be in Canvas, proctored with honor lock, and there will be 2 assignments just like last time. There will be one that has the questions where you go to take the test, and there will be one where you go in and submit your work. So the structure will be the same overall. Now, I am thinking about changing it a little bit to be weighted more towards the free response questions rather than the multiple choice questions. The multiple choice and true false questions are a little bit savage in the sense that, you know, they're either right or wrong. So either you get 3 points or 0 points for a multiple choice question. And after a few conversations with students and a little bit of consideration, I feel that the desire to have more free response is a reasonable and valid desire. So it'll probably be a little bit more like 3 multiple choice, or sorry, 3 true false. Maybe something like 3 to 5 multiple choice, somewhere around there. And then like 5 to 7 free response. I would rather see more of what you know, and I have no problem, you know, assigning partial credit. I actually prefer free response questions myself. So this is going to be approximately the layout. The true false are worth 2 points still. The multiple choice are worth 3 points each. And the free response are still worth 5 points. I do not think that we will be doing any rewrites. I do not plan to do any rewrites for exam 2. So that's the structure, the sections covered. These will be, flip your syllabus here. Let's see. All right, so 3.4. Let's do this 3.4, which is the chain rule. 3.5, 3.6. Which are on implicit differentiation and log derivatives. 3.9, 3.10, and 4.1. Related rates, linear approximation, min-max problems. 4.2, 4.3, 4.4, and 4.5. There will be a sprinkling of these. We will definitely have 4.1, 4.2, 4.3, and then 4.4. I have to remind myself what 4.4 even is. 4.4. Oh, indeterminate forms of L'Hopital's. Yeah, of course, that's what we're talking about today. And then 4.5. Okay. So those are the topics. Let's see. So 3.4 is chain rule. 3.5 was implicit differentiation. 3.6 is log derivatives, which included that logarithmic differentiation technique where you take the log before you differentiate. 3.9 is related rates. And what was 3.10? 3.10 is linear approximation, yeah. Um, 4.1 was on, sorry, my brain is not together this morning. 4.1 is min-max stuff. 4.2 is on the mean value theorem. 4.3 is on derivatives and the shape of the graph. 4.4 is on L'Hopital's rule, which we're going to talk about today. And 4.5 is a summary of curve sketching techniques. And a lot of your study guide is going to come from 4.5. 4.5 doesn't actually have anything new. The things I would pay extra careful attention to if I were you, 3.4, 3.5, 3.9, 4.1, 4.3. These are the super important topics here. Of course, the chain rule is a differentiation technique. You gotta have this shit down because we use it everywhere, especially here in implicit differentiation and here in related rates. The log derivatives and linear approximation are both important, and there may be a question or two on the test there that have something to do with those. But they're not as important as the other topics. Min-max problems are a huge deal. Finding local mins, local maxes, absolute mins, and absolute maxes, one of the primary tools in calculus. So this is a huge deal. Definitely expect at least one, probably more than one problem on this particular section. The mean value theorem, I may or may not sneak something in there with that, but I've shown you the types of problems that I enjoy from those. And there's really only one or two types of problems. You have them in your homework if you want to practice them. Mean value theorem, at least some reference to it. I would say here, make sure you know the exact statement of the theorem. So make sure you remember, oh, it says if f of x is continuous on the closed interval AB, differentiable on the open interval AB, then there exists some C in the open interval AB such that f primed of C is equal to f of B minus f of A over B minus A. Make sure you know the exact statement and make sure you can draw the related picture. As long as you can do that, you'll be good here. Derivatives in the shape of the graph. This is the majority of the homework this week. This is a huge deal, just like min-max problems are a huge deal. L'Hopital's rule we'll talk about today is fairly straightforward. There will probably be a problem relating to L'Hopital's rule because I would be doing a bad job as a teacher if I didn't, because you use it a lot in Calc 2. But then the summary of curve sketching, this is also pretty important. I would go ahead and star this. So next Friday is the test, but all next week before Friday, we'll be working out of 4.5. Like I said, nothing new here. It's really just a redo of 4.3 with a little bit of like extra focus on making you draw graphs by hand. And I will be making you draw graphs by hand on this test. So please practice that. Okay. Questions about the format of the test, when the test is taking place, what's expected of you regarding the test, anything like that?
Yes, Professor, I have a question.
Sure, go ahead.
So I start an internship on Monday and it's from 9 a.m. And on Friday, I have a meeting at the time of class, meaning during the test. Is there any way that I can take the test either before or after class time, or how would that work?
So if you have a conflict that is unavoidable, and it sounds like that one may very well be, send me an email or a Canvas message and we will figure something out.
Perfect. Thank you so much, Professor.
Yeah, of course. Any other issues or concerns along those lines, guys? Yeah, anything else like that?
I mean, I'm going to try to talk to them, but if they say like I have to go, then I'll email you.
Yeah, okay, of course. Sorry, yeah, the fuck it wasn't for you. I was fiddling around with something in the back of the computer. You're good. So this is the test. The study guide is going to come out today. And remember, I encourage you to work the study guide problems right away and send a sample of your work to me so we can discuss a little bit what looks good, what needs help, especially if you didn't do that before exam 1. I strongly recommend doing it before exam 2. But we do have some material to cover today. So I'm going to go ahead and get started on that. L'Hopital's rule is a funny topic. This is a Hopital, clearly a Frenchman. The symbol over the O is called an accent circumflex. It kind of takes the place of an S following the O, so some people remember this as the hospital. That's fine. What it is it's a technique for taking limits that are kind of difficult. So I'm just going to give you the statement of the theorem, and then we'll jump in and see why it's useful and get some practice. This says if f of x and g of x are both differentiable at x equals c, and the limit as x approaches c of f of x over g of x looks like 0 over 0 or infinity over infinity. And that these kind of quote bunnies here, where I'm surrounding the 0 over 0 and the infinity over infinity in quotes, is my way of saying like this symbol is kind of a nasty thing and I'm not really willing to take responsibility for it. But if f of x goes to 0 and g of x goes to 0 as x goes to c, so the top and bottom both look like 0, or the top and bottom both look like plus or minus infinity, these could be positive or negative, then we don't really know what they are. Right? Like we've seen that the limits which define the derivative all look like this until you do some algebra. L'Hopital's rule gives us a trick for taking limits like this. It says, if this is the case, then shockingly, one way to do this is to take the derivative of the top and the derivative of the bottom separately. So you're not differentiating the ratio, you're not differentiating the whole thing, you differentiate top and bottom separately and try again. Kind of weird, right? So objects like this, 0 over 0 and infinity over infinity, are called indeterminate forms. And actually the full title for the section here is L'Hopital's rule and indeterminate forms. So if you're trying to take a limit of a ratio and the limit at a glance appears to be 0 over 0 or infinity over infinity, then you can differentiate the top, differentiate the bottom, and try again. There are limits that we already know how to take, which fall to this. Like this. I know that if I plug in 1, the top is 0 and the bottom is 0. So by L'Hopital's rule, right? So this is indeterminate. We don't know. 0 over 0 could be anything. It's definitely not 1. You can't divide by 0 downstairs. Dividing by 0 downstairs we know is not allowed, right? Gives you something which is not a real number. But the thing upstairs is also 0. So these guys are kind of racing against each other to go to 0. And the question is, who gets there faster? So since this is an indeterminate form of the form 0 over 0, L'Hopital's rule says you can differentiate the top you can differentiate the bottom and try again. The derivative of the top here is 2x. 2x. And the derivative of the bottom here is 1. So if you send x to 1 in 2x over 1, you get 2 times 1, which is 2. And if you remember from exam 1, this was actually one of the limits you needed to calculate for question 11. You don't need L'Hopital's rule for this, right? We could do this without L'Hopital's rule by factoring the top. This is how we learned to take this limit way back in chapter 2. But now we have a new trick. We have this L'Hopital's rule trick. And the reason we teach it here is twofold. First, back then we didn't know how to take derivatives. We wouldn't have known what the hell this meant. But also because this rule allows us to do stuff that we couldn't do like this. And I'll give you some examples in just a second of limits for which L'Hopital's rule is absolutely necessary. First, any questions about the individual step here? What we actually did here, how we applied the theorem.
Do you only apply the theorem when it's like an indeterminate there?
We can definitely only apply L'Hopital's rule to indeterminate forms, but more specifically, we can only apply L'Hopital's rule to indeterminate forms that are 0 over 0 or infinity over infinity. There are other indeterminate forms, and that's one of the things we're going to talk about today is the other sorts of indeterminate forms which exist. But in order to apply L'Hopital's rule to a problem, it must be a limit looking like 0 over 0 or infinity over infinity.
All right, cool, nice.
Other questions on this?
Can you scroll down?
Yes.
Thanks.
Yeah, so then down here is the solution without L'Hopital's rule. This is how we would have taken that limit prior to today. Okay. So what is an indeterminate form? We're going to look at more L'Hopital rule examples in just a second. But before we do that, I want to ask and answer this question. It's any expression whose value cannot be discerned from the symbols used to write it. For example, we call 0 over 0 an indeterminate form. Because on the one hand, the limit as x goes to 0 of 2x over x, that looks like 0 over 0 because the top and bottom are both going to 0. But you can cancel the x's. This is equal to lim x to 0 of 2, which is 2. But also, the limit as x goes to 0 of x over 3x. This also looks like 0 over 0, because the top and bottom, they're both going to 0 as x goes to 0. But again, you can cancel the x's. And you see that this is 1/3. So 0 over 0 could be 2, or it could be 1/3. So from the symbols 0 divided by 0, you cannot tell what this thing is going to come out to. Here 0 over 0 is equal to 2. Here 0 over 0 is equal to 1/3. The statement 0 divided by 0 does not encode enough information to discern the value of the expression. So that is called an indeterminate form. Anytime you see 0 divided by 0, it should set off an alarm in your head like, ah, shit. You know, maybe there's some algebra I could do to clean this up so that it doesn't look like 0 over 0 anymore. An important note you cannot cancel the zeros. It's not true that 0 over 0 is always equal to 1. Algebraically, right? And again, here's an example where 0 over 0 is 2. 2 is definitely not the same as 1. Here's an example where 0 over 0 is 1/3. 1/3 is definitely not 1. So you can only cancel things top to bottom in a fraction if they're non-zero factors that are shared between the top and the bottom. So don't ever try to cancel 0 over 0. Infinity over infinity is another example of an indeterminate form. And I could actually use the same two examples that I had there, but let me use another one here. So let's say the limit as x goes to infinity of 2x squared minus 3x plus 1 over, how about 5x squared minus 3. Here, the top is definitely going to infinity as x goes to infinity. And the bottom is going to infinity as x goes to infinity. And just like you can't cancel the zeros, you can't cancel the infinities. What's wrong, Bubba? You okay? We saw back in section 2.6 how to handle things like this. We divide through top and bottom by the largest power of x. And then each of these little pieces goes to 0. So we have 2 minus 0 plus 0 over 5 minus 0. In this case, infinity over infinity comes out to 2/5. And I could build lots of things like this, which look like infinity over infinity, but when you renormalize, you get out 2/5. So 0 over 0 and infinity over infinity are two expressions whose value cannot be discerned from the symbols we use to write them. So in other words, we try to avoid writing 0 over 0, and we try to avoid writing infinity over infinity because they don't actually really mean anything. 0 over 0 could be literally any number. It could be -1, it could be pi, it could be 5, it could be 0, it could be 12, it could be infinity. So 0 over 0 on its own doesn't have any meaning. Neither does infinity over infinity. And for that reason, we call them indeterminate forms, but they're not the only ones. These are the two indeterminate forms to which we can apply L'Hopital's rule. But there's a bunch of other indeterminate forms. Can anybody think of another expression like that, where from the symbols you use to write it down, we can't say for sure what the value is?
Absolute value?
Well, what if I take 0 and I multiply by infinity? So this 0 times infinity is another indeterminate form. So you've got something really, really, really small multiplying something really, really, really big. An example, a specific example here might be something like limit x goes to infinity. What would be a good one here? How about e to the negative x times e to the positive x. As x goes to plus infinity, e to the negative x goes to e to the negative infinity, which is 0. And e to the x goes to e to the positive infinity, which is infinity. So this looks like 0 times infinity. Now in this case, so this doesn't tell me anything. But if I do some algebra, that's the same as the limit as x goes to infinity of 1 over e to the x times e to the x over 1, I can cancel these. I just get 1. So in this case, 0 times infinity is 1. But also, I could say, look at the limit as x goes to, how about 0 of x squared times, let's look at the limit as x goes to 0 plus x squared times 1 over x. As x goes to 0 from the right, x squared definitely goes to 0. And 1 over x goes to plus infinity. So this also looks like 0 times infinity. But in this case, if I do some algebra, I get x squared over x, which is the same as just good old x. So here, 0 times infinity is equal to 0. Here, 0 times infinity is equal to 1. So 0 times infinity is indeterminate for the same reason that 0 over 0 and infinity over infinity are indeterminate. Because there's lots of things that you can say are equal to 0 times infinity that come out to different values, right? Is it 1 or is it 0? And the answer is it's neither of those things necessarily, it's an indeterminate form. So from the symbols 0 and infinity, you cannot tell me what 0 times infinity is. And in all of these cases, you've seen me just doing some algebra to simplify the limit and actually get the correct value out. There are other indeterminate forms. I'm not going to keep writing down lots of examples, but other indeterminate forms. What you have to look for are two things that are kind of fighting each other, like 0 and infinity are fighting each other when you multiply them, because one wants to be very small, the other wants to be big, and when you multiply them, they don't know who wins. Other things like that are infinity minus infinity, 0 to the 0, 1 to the infinity. And let me see if I'm missing any others. I should have a list here. Maybe not. Internal powers. Ooh, no. Wow, they really don't. Okay, so I think there's one or two others. Yeah, what do we got? 0 over 0, infinity over 0, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity. Oh, yeah, I knew I was forgetting one. Infinity to the 0. All right. So anytime you see an expression like these, and I'll just to make the list complete, include the other ones here. We had 0 over 0, infinity over infinity, 0 times infinity. Anytime, sorry, I'll take care of my dog. Anytime you see anything like these, you know you have more work to do. You cannot conclude just from those their value. Yeah. L'Hopital's rule is a trick to allow us to handle indeterminate forms. The trick is, or the problem is, that L'Hopital's rule can only handle 0 over 0 and infinity over infinity. So if you have something like 0 times infinity or infinity minus infinity, then you'll have to do some sort of algebra to get it into the form 0 over 0 or infinity over infinity before you can apply L'Hopital's rule. However, L'Hopital's rule is a little bit nasty. So before you even consider doing L'Hopital's rule, you should try doing what I did in each of these examples and just cleaning things up algebraically. If you can use some algebra to figure out your limit, that's always preferred to L'Hopital's rule. All right, let's calculate some limits. As x goes to plus infinity, what does x do? What does my numerator go to? And what does e to the x do? What does my denominator do? What does this limit look like?
Infinity over infinity.
Yeah, top and bottom both getting big. So this looks like infinity over infinity, which means I can use L'Hopital's rule. And since there's no way to factor an x out from e to the x, I know that there's no algebra I can do here to clean this up. So I have to use L'Hopital's rule here. And the way I like to let my reader know that I'm using L'Hopital's rule, rather than writing out all the words by L'Hopital's rule, I just, above my equal sign, put a little LH. That way my reader will know that I'm taking the limit using L'Hopital's rule. So I differentiate the top, I differentiate the bottom, and then I try again to take my limit. The derivative of the top is 1. What's the derivative of the bottom?
E to the x.
They say.
Yep. So now what's going on? Well, the top stays 1, the bottom is still going to infinity. This is no longer an indeterminate form. This is 1 over infinity. That's 0. Neat, right? Let me try one more like this, and then we're going to do something else. How about x cubed over e to the x? We're still in the same position here, where the top is going to infinity as x goes to infinity, and the bottom is going to infinity. And I like to put this in the little quote bunnies to say I'm not responsible for it. You know, I know this isn't a real number. But since it is of the form infinity over infinity, I can attempt to clean it up with L'Hopital's rule. So I'll take the derivative of the top and the bottom. The derivative of the top is 3x squared. The derivative of the bottom is still e to the x. But this still looks like infinity over infinity. The top is still going to infinity. The bottom is still going to infinity. So I need to use L'Hopital's rule again. So if I take this guy and I differentiate the top and I differentiate the bottom, I'll get 6x over e to the x, which still looks like infinity over infinity. So one more attempt with L'Hopital's rule. The top will differentiate to 6, the bottom still e to the x. So you get 6 over infinity, which is 0. So you can kind of think of this as a race. The top is trying to go to infinity and the bottom is trying to go to infinity. And the question is sort of who gets there faster? And remember, derivatives are rates of change. So thinking about this as a race between the top and the bottom is really a pretty good analogy. When you differentiate the top, you get his rate of change. When you differentiate the bottom, you get his rate of change. And because the function downstairs grows so much faster, has a much larger rate of change, this first example still comes out to 0. So e to the x grows so much faster than x that this limit is 0. And the same is true comparing x cubed and e to the x. E to the x grows so much faster than x cubed that this limit still comes out to 0. But x cubed grows faster than x. So it takes a few applications of L'Hopital's rule to get us there, rather than just the one. Some of the special trig limits that we looked at from earlier in the semester. The limit as theta goes to 0, sine theta over theta. This looks like 0 over 0, because if you just plug in, you get sine 0 over 0, but the sine of 0 is 0. So we can use L'Hopital's rule. Differentiate the top, differentiate the bottom. The derivative of the top is cos theta. The derivative of the bottom is 1. And as theta goes to 0, cosine of 0 is 1. And you may remember that this special trig limit was 1. That was one of the important limits we needed when we cooked up the derivative of the sine function. Questions on this set of examples here? These all feel pretty okay? I don't want to spoil that for you. That's a fun problem. Yeah, let's look at a product next. I'll have to go to 0 plus, yeah. Okay, no questions on any of these? You guys sure? Really comfy with all this stuff?
Semi-comfy.
Say that one more time, I'm sorry.
Yeah, semi-comfy, not really comfy.
Semi-comfy, okay. Okay, well then let's look at something else. So what if I wanted to take the limit as x goes to 0 from the right of x times the natural log of x? So what does the natural log of x do as x goes to 0 from the right? Let's look at that piece first. Sorry. What does this guy do as x goes to 0 from the right? Scaring me a little bit. The natural log function has a graph, remember, looking like this. So as x goes to 0 from the right, ln x on his own goes down to negative infinity. And of course, the x piece is going to 0. So this is 0 times negative infinity, which is an indeterminate form, but it's not an indeterminate ratio. It's not 0 over 0 or infinity over infinity. So I can't apply L'Hopital's rule right away. This is indeterminate. But we can't use L'Hopital because it's not 0 over 0 or infinity over infinity. So does anybody have any idea how I could take something like this and rewrite it as something like this? Or how could I take x times ln x and rewrite it as a fraction where the top and bottom are both going to 0? Or as a fraction where the top and bottom are both going to infinity?
You use a product rule.
Well, I'm not trying to differentiate anything, remember? I'm just trying to take a limit. If I wanted the derivative of x ln x, that would definitely be a product rule thing.
Can we do all of this over x?
I think I'm hearing the right idea there. I can pick one of them to leave upstairs, and the other one I can stick downstairs as his reciprocal. So I could, for example, leave the natural log of x upstairs and say, oh, x is the same as 1 over x. So x times ln of x is the same as ln of x divided by 1 over x. Is everybody following this? So algebraically, this is equivalent to this. Just do the flip and multiply thing, right? If you flip this and multiply, you get this. So this is the same as this. I haven't changed anything. I've just rewritten it. But now, if you try and take the limit as x goes to 0 plus ln x goes to negative infinity, 1 over x goes to positive infinity, that is an indeterminate ratio of the form that I can use L'Hopital's rule on. So now if I apply L'Hopital's rule, I'll get the lim as x goes to 0 from the right. The derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. And if I just tried to plug 0 in again, I would get infinity over infinity, but I can do some algebra. That's negative x squared times 1 over x, right? Or negative x squared over 1 if you prefer. Cancel a copy of x, and you get the limit as x goes to 0 from the right of negative x, which is negative 0, which is 0. So this limit is 0. But we couldn't apply L'Hopital's rule right away because this was an indeterminate product. And L'Hopital's rule only applies to indeterminate ratios.
So the list you gave us, 1 to the infinity, infinity minus infinity, and 0 times infinity, we have to do algebra before using L'Hopital's.
Exactly.
Cool. Okay, thank you.
Yeah, if you have an indeterminate form that is not 0 over 0 or infinity over infinity, we have to do some amount of algebra to turn it into that, then apply L'Hopital's rule. Okay, so I'll push this up here, so if you're still writing, you can continue to write. but I want to talk a little bit more generally about how to handle indeterminate products like these. So 0 over 0 and infinity over infinity, these are indeterminate ratios. We can use L'Hopital. Remember, ratio is just a word for fraction. 0 times infinity, this is called an indeterminate product. And here we can't use L'Hopital's rule right away. And the way you do that is you take your functions, you'll have two functions, f times g. One is going to 0, the other is going to infinity. And you'll rewrite that either as f of x divided by 1 over g of x, or g of x divided by 1 over f of x. So if f was going to 0 and g was going to infinity, then f times g looks like 0 times infinity. But if I rewrite it like this, then the top is going to 0 and the bottom is going to 1 over infinity. Oh, well, that's 0 also. So this would now look like 0 over 0. Or if you chose to rewrite it the other way, and you always have a choice, back in this problem, I could have rewritten this as x divided by 1 over ln x. If you do it the other way, so the top is going to infinity and the bottom is now going to 1 over 0. Oh, well, that's infinity over infinity. So you can always rewrite it either as a ratio that goes to 0 over 0 or a ratio that goes to infinity over infinity. And the way I usually choose is by asking which one do I want to differentiate as it is, and which one would I want to differentiate the reciprocal of. If f is easy to differentiate, and g's reciprocal is easy to differentiate, then I'll rewrite it as f divided by 1 over g. And conversely, if g is easy to differentiate on its own, but g's reciprocal is not easy to differentiate, and f's reciprocal is easy to differentiate, then I would rewrite it like this. So what about indeterminate differences? Infinity minus infinity. This is called an indeterminate difference. And we can't use L'Hopital right away here either. So here you have something like f of x minus g of x, and they're both going to infinity. The way I would handle something like this is usually by multiplying, f of x minus g of x. Usually I'll multiply by something like f of x plus g of x over f of x plus g of x. It's like that multiply by the conjugate trick that you learned back in algebra, you also used in trigonometry. So now my numerator will be going to something hopefully a little bit nicer. It'll be like f squared minus g squared, and my denominator will be going to something hopefully a little bit nicer. Like if f and g are both going to infinity, then f plus g is definitely going to infinity. So if you're lucky, this will look like infinity over infinity when you're done, and then you can use L'Hopital's rule. The ones we haven't dealt with, indeterminate powers, like 1 to the infinity and 0 to the 0. Again, we can't use L'Hopital's rule right away. Here you have something like f of x being raised to the power of g of x. And maybe f is going to 1 and g is going to infinity, or maybe they're both going to 0, something like that. Here we take logs. And then we try to rewrite as a ratio. So the indeterminate powers tend to be the trickier ones to do. So I think I'll do one of those next. And then if there's time, I'll do an indeterminate difference. If I look at the limit as x goes to 0 from the right of x to the x. Remember, x to the x is kind of a strange function. We took his derivative back when we were in the logarithmic differentiation section. And we saw that to take his derivative, we had to take the ln and then differentiate implicitly and then solve for the derivative. Here, we're going to require something different. So this, at a glance, if you just plug in 0, looks like 0 raised to the 0th power, which is definitely indeterminate. It's an indeterminate power. So what I'm going to do instead is I'm going to say I'll let y equal x to the x. Then take logs. So the ln of y is the ln of x to the x. And my goal is to recover the limit as x goes to 0 plus. But first, I'm going to use my rules for logarithms to rewrite this as x times the ln of x. Remember, one of my rules for logarithms is that powers inside can come down as multiples out front. So now if I look at the limit as x goes to 0 plus of x ln x, this is something we did earlier. This looks like 0 times negative infinity, which is an indeterminate product. So I rewrite him as a ratio. As ln x divided by 1 over x. And if we try and take the limit now, I get negative infinity over positive infinity, which is an indeterminate ratio. So now I can use L'Hopital's rule. So now I can finally use LH. And when I do that, again, the derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. We've seen that this simplifies to the limit as x goes to 0 plus negative x squared over x, which is the same as the limit as x goes to 0 plus of negative x, which is 0. So the natural log of y has limit the 0. Therefore, y has limit e to the 0, which is 1. In other words, the limit as x goes to 0 plus of x to the x is 1. So this is one of the simpler examples of an indeterminate power, but it's still not simple. And I think it would probably be wise to look at one more. First, questions on what we did here. Yeah, I see something in chat here. What's that? Show how I differentiate 1 over x. Oh, sure. So the derivative of 1 over x, I'm treating that as d dx x to the -1, which by the power rule is -1 times x to the -2, which is -1 times 1 over x squared, which is -1 over x squared. Yeah, that's how I'm calculating that derivative. Other questions on this fellow? Can you always use negative infinity for ln x? Well, again, remember that's coming from the graph of the natural log. So ln x goes to negative infinity only as x goes to 0 from the right. Yeah, so as x goes to 0 from the right, the natural log dives down to negative infinity here. But if you're taking a limit somewhere other than 0 from the right, ln x will not go to negative infinity. So it totally depends on where you're taking the limit. But yeah, as x goes to 0 from the right, ln x does always go to negative infinity. That's true. Okay, let's try one more example of an indeterminate power. The indeterminate differences, I think, are not too bad. I would rather give you a little bit more practice with these since they tend to be tougher. How about the limit as x goes to infinity of 1 plus 2 over x raised to the 3x power? This may look familiar, but it may not. If you remember the definition of the number e from your pre-calculus class, this should look at least somewhat similar to that. If we plug in infinity, then this is 1 plus 2 over infinity raised to the 3 times infinity. 1 plus 2 over infinity, that's 1 plus 0, and 3 times infinity, that's definitely infinity. So this looks like 1 raised to the power of infinity, which is an indeterminate power. So just like in the last problem, I'm going to let y be 1 plus 2 over x raised to the 3x. I'll let y be my function. I'll just give it a name. And then I'm going to take natural logs on both sides. And then I can use my properties of logarithms to rewrite the left-hand or the right-hand side as 3x times the natural log of 1 plus 2 over x. And this process of taking logs, so now the limit as x goes to infinity of y is, ln y. So now the limit as x goes to infinity of ln y is the limit as x goes to infinity of 3x times the natural log of 1 plus 2 over x. The 3x piece is going to infinity. The natural log piece is going to the ln of 1 plus 0. That's the ln of 1. That's 0. So this piece goes to infinity. This piece goes to 0. And that's an indeterminate product now. So I'll rewrite my product as a ratio. That's the ln of 1 plus 2 over x divided by 1 over 3x. Right? Multiplying by 3x is the same as dividing by 1 over 3x. And now if we try to plug in infinity, I get 0 over 0. The ln is still going to the ln of 1. The bottom now is going to 1 over infinity, both of which are 0. So now and only now can I apply L'Hopital's rule, which says differentiate the top, differentiate the bottom separately, right? Each on their own. The derivative of the natural log of 1 plus 2 over x is 1 over 1 plus 2 over x times the derivative of 1 plus 2 over x. Well, 1 differentiates to 0 plus 2 over x is 2 times 1 over x. So he will differentiate to negative 2 over x squared. And then my denominator, 1 over 3x, if I differentiate him, I will get negative 1 over 3 times x squared. Again, here I'm using the power rule. I pop out the 1/3. That's 1/3 times d dx of 1 over x. And the derivative of 1 over x we saw was negative 1 over x squared. So that's negative 1 over 3x squared. And the derivative of the logarithm piece we did pretty carefully. The derivative of 2 over x goes the same sort of way. You just pop out the 2, and then 1 over x differentiates to negative 1 over x squared. So this looks pretty nasty, but I can do some algebra and clean it up. I'll leave this guy alone. This piece here is negative 2 over x squared. And then this piece downstairs, I can bring him back up now as negative 3x squared over 1. And I can cancel the x squareds. So I get lim x to infinity 1 over 1 plus 2 over x times negative 2 times negative 3, like so. This piece is going to 1 over 1 plus 0. And then you've got your negative 2 times negative 3. So that's 1 times negative 2 times negative 3, which is positive 6. Therefore, the ln of y has limit 6, which implies the limit as x goes to 0 plus of y is e to the 6. So my limit (1 plus 2 over x all raised to the 3x), that's e to the 6. So take a second to make sure your notes have all the good stuff here. And then let's see what questions we have. Questions about recognizing this as an indeterminate power. Let's start there. Any questions about why this comes to 1 over infinity or why that is an indeterminate power? I would like to say that 1 raised to any power is 1, but the inside here isn't always 1. It's 1 plus something very, very small. So when you raise 1 plus something very, very small to a huge power, that very, very small piece actually can contribute quite a bit. Since it is an indeterminate power, my procedure is to call the thing y and take the natural log on both sides. Over here, the natural log of this power, I can bring that exponent down in the front. Having done that, I check again and see what the limit is. So I take the limit again in this form, and I get infinity times 0. And I'm like, ah, shit, that's still an indeterminate form. But I've gone from an indeterminate power to an indeterminate product. So I'm kind of going from a hard problem to a less hard problem. Indeterminate products, I know how to handle those. I rewrite them as a ratio. So I pick one of these pieces to go downstairs. Differentiating this on its own is kind of a pain in the ass. I really don't want to differentiate the reciprocal of that. So I shove this one downstairs instead. So I shove the 3x downstairs as 1 over 3x. And I note that if I take the limit again, I get 0 over 0. The natural log of 1 is 0, and 1 over 3x as x goes to infinity, that's also 0. So now I'm like, hooray, indeterminate ratio. That's the thing I wanted. Now I can use L'Hopital's rule. The differentiation is a little bit rough. Remember that to differentiate any natural log, I have 1 over the inside times the derivative of the inside. So here's 1 over the inside of my log times, here's the derivative of the inside of my log. And then downstairs, I differentiate that guy on his own also, and I get this.
Excuse me, sir.
Yes.
Yeah, 1 over 3x. When we derive it, so it should give 1 over x squared. Can you explain to me? So I don't remember exactly the formula.
So I'm popping the 1/3 out, and then I differentiate the 1 over x. So 1 over 3x is 1/3 times 1 over x.
Okay.
Third comes out, and then the derivative of 1 over x is negative 1 over x squared, and then I recombine.
All right, thank you.
Yeah, of course. And then the derivative of the top is pretty similar, only I have to use the chain rule with the natural log stuff. So I have 1 over the inside of the log. This is the 1 over u piece. And then I have the u prime, the derivative, the derivative of the inside. That's this piece. And then I just clean this up algebraically. I bring this guy back upstairs by flipping and multiplying. And the x squareds cancel, which is nice because it's those guys which is giving me trouble. So now that they cancel, this piece is clean. This piece is going to go to 1 because 2 over x goes to 0. And the -2 times -3 gives me 6. So this piece goes to 1. I'm not worried about him. I've got -2 times -3 after the x's cancel. -2 times -3 is +6. And then I just have to stop and remind myself what it is I was doing. I wasn't working directly with my function. I was working with the natural log of my function. So if the natural log of my function goes to 6, then you can exponentiate on both sides to conclude that my function has to go to e to the 6. other questions on this fella? So there's a few problems like this in your homework, and these are going to be the hard ones. All right, from L'Hopital's rule, these are going to be the hard ones, the indeterminate powers. We did 2 examples here, and if you look at the Paul's online math notes page for L'Hopital's rule, you'll see him having several more examples there. You can look at those if you get stuck on your homework. We did get started late today, so I want to do one example of an indeterminate difference. If you have to go, I understand, but I will ask that you hang around for just a second to see one more example. And that way, we've seen one of everything. How about a fun one? Yeah. The limit as x goes to 1 from the right, 1 over the natural log of x minus 1 over x minus 1. As x goes to 1 from the right, the natural log of x goes to 0. And as x goes to 1 from the right, 1 over x minus 1 goes to 1 over 0. And since we're going to the right, this 0 is really like a positive, and this guy is also positive. So this is infinity minus infinity. Both infinities are positive. Because the denominators stay positive as we go to 1 from the right. If we're going to 1 from the left, the natural log would still go to 0, but it would be going there and all of the nearby values would be negatives. So this would be a 1 over 0 minus, which would be a negative infinity. And the same is true here. If we went to 1 from the left, this would go to 1 over 0 minus, which would be a negative infinity. It would still be an indeterminate difference, but the signs would be swapped. The first one would be negative, and then you'd have minus, a negative would make a positive. So we've got some choices as to how we could try to handle this. One of the options that you have when you see an indeterminate difference, and honestly the most common one, is to multiply by the conjugate. But here, this doesn't really look like a multiply by the conjugate thing because I've got 2 little fractions inside there. And anytime somebody tells me to subtract 2 fractions, I know what to do. I have a common denominator. So let's just see what to do with that. I'm trying to subtract 2 fractions and figure out what the hell this thing does. So let me go ahead and have a common denominator between these. Here I multiply by x minus 1 over x minus 1. Here I multiply by ln x over ln x. So if you have a common denominator, then it starts to look like this. Now what does this look like? Well, x minus 1 is going to 0. ln x is going to 0, so that top is going to 0 minus 0, which is 0. And downstairs, this is 0 times 0. That's also 0. So I go from an indeterminate difference to an indeterminate ratio. And the indeterminate ratio, I can now apply L'Hopital's rule to. So I'll differentiate the top and I'll differentiate the bottom. The derivative of the top here, the derivative of x is 1. The derivative of 1 is 0. And the derivative, I'll write it like this. And the derivative of ln x is 1 over x. Downstairs, I need to use the product rule. I have no choice. I'm differentiating the bottom, but the bottom is a product. So I'll differentiate this, leave this alone. That's 1 minus 0 times ln x plus, I'll leave the x minus 1 alone and differentiate the ln x. So that looks like this. And now I need to do some more algebra. First, let me just throw away the zeros. That's 1 minus 1 over x, all divided by ln x plus, let me distribute here, 1 minus 1 over x. I can't cancel anything because I would have to factor in order to cancel. There are no common factors top to bottom. So I have a common denominator upstairs, a common denominator downstairs. And I get, actually, here's a faster way to do this. I could multiply top and bottom by x. So I'll get x minus 1 over x ln x plus x minus 1. And now I see if things have gotten better. As x goes to 1, x minus 1 still goes to 0, so the top is 0. X ln x goes to 1 times 0, that's 0. And then x minus 1 also goes to 0. So this is still looking like 0 over 0. So I apply L'Hopital's rule again. The derivative of the top is now 1. The derivative of the bottom, this piece will require a product rule. I'll have 1 times ln x plus x times 1 over x. That's the derivative of x ln x. Plus the derivative of x is plus 1. And then minus 1, he differentiates to 0. All right, and if you wanted to, you could write the derivative of this 1 as 0 there too. Once again, I'll clean up algebraically. The numerator is now just 1. The denominator is ln x plus x times 1 over x is plus 1. And then this piece is also a plus 1. So this looks like the limit as x goes to 1 plus 1 over ln x plus 2. As x goes to 1, ln x goes to 0, so this is 1 over 0 plus 2, or 1/2. And now we're done. So this is another example of a problem that requires 2 runs of L'Hopital's rule. Like we saw the x cubed over e to the x requiring 3 runs earlier. Here I had to use L'Hopital's rule at 2 different steps, here and here. And in between, I did a bunch of algebra to simplify things. My first step was having a common denominator. So I recognized that this is an indeterminate difference. And in a sense, these are tricky because there's no set rule for what to do. But I had a difference of 2 fractions. So my intuition is to combine them as a single fraction. So I have a common denominator. Multiply by x minus 1 over x minus 1 in the first piece. Multiply by ln x over ln x in the second piece, and I get this. This looks like 0 over 0 as x goes to 1. So now I apply L'Hopital's rule. The derivative of x is 1. The derivative of 1 is 0. The derivative of ln x is 1 over x. The derivative of the top is 1 minus 0 minus 1 over x. The derivative of the bottom requires the product rule. So first I differentiate x minus 1. I leave ln x alone. And then I add that to what I get when I leave ln x alone and differentiate, I leave x minus 1 alone and differentiate ln x. Then I just clean it up. So I get rid of the 0 stuff, distribute my 1 over x here. 1 over x times x is 1. 1 over x times 1 is 1 over x. And I try to take my limit again. But what I see is that I'm still getting 0 over 0. Okay, that just means it's time for more L'Hopital's rule. The derivative of the top is 1. The derivative of the bottom has this little product rule in it from the x ln x. The derivative of x is 1. The derivative of 1 is 0.
I have a question.
Yeah.
When you did the first L'Hopital's rule up there, is that 1 times 0 times the natural log of x?
1 minus 0.
That's what I thought. Okay.
Yeah, so that's coming from the little product rule.
Yeah.
In that little product rule, I had to differentiate x minus 1.
Mm-hmm.
This is the derivative of x. Yeah, sorry, I tried to zoom in to make that a little bit more clear, but I see that it's not. So this is 1 minus 0, and it's coming from the derivative of x minus 1. So the derivative of x is 1, the derivative of 1 is 0. So x minus 1 differentiates to 1 minus 0.
Perfect. And then that's 1 natural log of x plus 1 minus 1 over x. Got it.
Exactly, yep. Okay, so yeah, our second run of L'Hopital's rule looks like this. Little product rule here, differentiating x ln x. Derivative of x here is 1. The derivative of 1 here is 0. And then x times 1 over x is 1. So I end up with a 1 plus 1 downstairs and an ln x downstairs. As x goes to 1, this guy is going to go to 0. So I just get 1 over 2. That's L'Hopital's rule. It's a neat trick, but it's just a trick. And you should always try to do algebra first. Think of L'Hopital's rule as a last resort. A lot of the limits that we care about will look like 0 over 0 or infinity over infinity. Because that's really what limits are useful for. Limits are useful for investigating kind of weird shit, right? If your limit looks like 0 over 0 or infinity over infinity, then you can apply L'Hopital's rule. But that doesn't mean you always should. And I point you back to the first like 3 or 4 examples we did in class today where I had indeterminate forms, but I was able to like factor and cancel, so I didn't need L'Hopital's rule. There's nothing inherently wrong with using L'Hopital's rule on those problems, but differentiation, calculus is harder than algebra. So if you can do the limit with algebra, do that. If you cannot sort out the limit by factoring and canceling, or if you do not see any way to clean things up algebraically, then you can go ahead and try L'Hopital's rule, but only if the ratio looks like 0 over 0 or infinity over infinity. If it's one of the other indeterminate forms, you have to bash it with the algebra hammer until it looks like 0 over 0 or infinity over infinity. The book has a proof of L'Hopital's rule. It's not bad, but it's not very insightful, so I don't want to burn your time on it. The last thing that we're going to talk about before the exam is that summary of curve sketching section 4.5. Like I said, there's nothing new in section 4.5. It's all talking about things that you've learned like way back in your algebra classes, domains, intercepts, symmetries, even and odd functions. Asymptotes, we talked about these in 2.6, and you also studied those in algebra. Increasing, decreasing, local mins, local maxes, concavity and points of inflection. This is the 4.3 shit that we've been talking about through the rest of this week. And then you draw the thing. That doesn't mean we don't need to spend time here. And my intent is next Monday and the start of class next Wednesday, we will be going through problems like this. But you need to finish the homework that includes the 4.3 stuff in order to have a reasonable discussion about 4.5. 4.3 and 4.5 are the two most important sections in this textbook, at least for Calc 1. So please, please, please sink a lot of time into the 4.3 homework. It's the one that's open right now, just the stuff before L'Hopital's rule and after mean value theorem. Make sure you're really comfortable finding mins and maxes, finding intervals of increase and decrease, finding intervals where you're concave up and concave down. And then we'll be able to talk about this stuff really well next week. It's amazing how good a graph you can get from this stuff. Like, look at this, x e to the x graph. This is a really cool example. You'll be able to draw this picture with all these important points labeled completely accurately. You remember in your pre-calculus classes when you were graphing rational functions and some of them had these like U-shaped pieces and WebAssign asked you to guess at the max or guess at the min. Now you're able to find those for sure. So that sort of stuff is where we are going to be going. I'm going to spend some time on this next week. You're going to have problems like these in your study guide. I will be releasing that study guide as soon as I can. My plan is to get it out a little bit later this afternoon. And then we'll move on from there. We'll be ready for the test. The test will be next Friday. Hopefully you'll be working on the homework and study guide problems over the weekend, over the week next week. We'll be able to talk about these sort of things to make sure you're nice and ready for the test on Friday. After that, we are going to talk a little bit about applied optimization. The syllabus has applied optimization on exam 2, but I'm going to push that to exam 3. And then we're going to start talking about integrals, which are the whole other half of calculus. Calculus can really be split into two chunks, differentiation and integration. Integration is what the last part of Calc 1 focuses on, and it's what about a full third of Calc 2 focuses on. So we will be spending our last few weeks in class talking about how to underive functions, how to go backwards in the differentiation chain. But for now, please work very hard on the homework that is currently open. Watch for the study guide to drop, and then as you have questions, don't hesitate to contact me, okay? Unfortunately, this afternoon, I do not think I will be able to hold my normal office hour, but I will schedule an extra one over the weekend or on Monday. I'll post a Canvas announcement about that a little bit later today. All right, I gotta run. I got another class to teach. I hope you guys have a lovely rest of your day. Again, any questions, don't hesitate to reach out with a Canvas message. Watch for the Canvas announcement telling you when the replacement office hour will be. Work hard on that homework, and when the study guide drops, start working on that also.
Hey, Professor.
Yeah.
I'm going to send you an email right now. So if whenever you get the chance, if you can please look at it.
Sure. Yeah, of course.
Thank you so much. Have a good day.
You too. You too. All right. I will see you guys either in the office hour over the weekend or in class on Monday. All right. Have a good afternoon.